Yeah, it is a graduate course of quantum mechanics. In the undergraduate course of quantum mechanics, it deals with Schrodinger equations and unbounded state like wave packet and potential well, potential barrier, and angular momentum, and as well as harmonic oscillator and hydrogen atom. But in the latter part of the quantum mechanics textbook, they may have the perturbation theory and hyperfine structure and identical particles and scattering and independent or dependent perturbation theory. Then, but that latter part not deals with in the undergraduate course. So in this course, then I will more focus on the latter part of the that undergraduate students didn't study. At first, I started from the perturbation theory. Basically, and in quantum mechanics, there are several undergraduate course examples like a hydrogen atom, and also there are several potential barrier and potential well. It is very simple problem, and then that can be calculated exactly. But in real practical calculation, and most of the system that cannot calculate exactly. So, and basically we know that the basic starting point is the Hamiltonian. And the Hamiltonian, and in perturbation theory, basic concept is that the Hamiltonian can be separated by the solvable Hamiltonian. We call it as H0, and also perturbation H prime. H prime is that not it is exactly solvable Hamiltonian, and H prime is the additional. And also in energy scale of H0 and energy scale for H prime, then the H0 should be high, because if we assume that it is tail, it is body should be heavy comparing to the tail, and if otherwise, and the tail can have a significant effect to the body. So, and this we call it as a part of the Hamiltonian. Part of the Hamiltonian, the energy scale should be very small comparing to the exactly solvable Hamiltonian H0. Here, basically, here is a basic assumption. Here, and here chapter 10 is not limited, because my textbook is the quantum mechanics by David McTire, and it is published to the Cambridge University Press, and in this case, and chapter 10. The quantum mechanics, the textbook is that quantum mechanics, and by David H. McTire, McIntyre. So it is published to Cambridge University Press. And actually, here we assume that this Hamiltonian can be separated by these two Hamiltonian, solvable and unsolvable, and we call perturbed Hamiltonian. And let's consider for the example. And one example is a spin 1/2 system. Let's assume that spin 1/2 electron is under the applied magnetic field. The applied magnetic field in G direction. Then the Hamiltonian, basically this Hamiltonian can be exactly solvable, and H0 is that minus mu dot B. Minus mu mu means that magnetic moment. Here magnetic moment, and so it can be write down as the omega 0 Sg. It is already studied here. Omega 0 is that the Raman frequency, and in the undergraduate course of quantum mechanics, and especially in the hydrogen atom, we calculate the omega 0 is that EV0 over ME. Here is Raman frequency, electron mass. It is Raman frequency. By a small calculation, and here the H0, if we apply magnetic field to the spin 1/2 system, and the Hamiltonian can be written like this, and because Sg it is a spin Hamiltonian like Pauli matrix, and so here in the G direction Pauli matrix is that the spin half and omega 0 0 0 minus omega 0, and here. So we know that here this energy eigenvalue here is we call 0. 0 means that exactly slope of energy, and plus minus spin up and spin down. The energy eigenvalue is that the plus minus 1/2 h bar omega 0. Here we call it as a zeroth order. Zeroth order of energy. But in general, and here we apply magnetic field in the fixed direction, and we set the fixed magnetic field direction as a z direction. But in general case, magnetic field can be directed in various fields, but here we denote like this. We assume that here B0G is that exactly solvable Hamiltonian can be associated with the exactly solvable Hamiltonian, and also B1G is the additional magnetic field, and also B2 is on the other axis. Here we assume that magnetic field is in the electromagnetic field, in the electric field and magnetic field, electric field and magnetic field correlate with each other from the Maxwell theory, and also propagating. It is S means that the pointing vector, and so here magnetic field is under the xy plane or the xg plane. Here we set the xg plane, and the xg magnetic field is under the is in the xg plane, and it is rotating. And also here G B0 is the exactly solvable term. By simple explanation, and here we can define that several other Raman frequency like EB1 over ME, or the omega 2 is that EB2 over omega ME, like this. And so here this general Hamiltonian is that mu dot B minus mu dot B. So it is that omega 0 Sg plus omega 1 Sg plus omega 2 Sx. Here from the Pauli matrix, here Sx is that 1/2 and 0 1 1 0. So from the here omega 0 plus omega 1 is that the Pauli matrix is that like this. Sigma g is that 1/2 1 0 0 minus 1, and so here it is 1/2 h bar, and omega 0 plus omega 1 and minus omega 0 plus omega 1, and also here Sx is that omega 2 and omega 2. So, and this Hamiltonian can be separated by the h0 plus h prime, and the h0 is that here it is h0 and it is h prime. It seems to be pi, but x. Then here, when we consider for basically in the general magnetic field, generally magnetic field can direct in any direction, and then it can be separated by the magnetic field along the g direction. Here is B0. B0 is that exactly solvable associated magnetic field, and also here additional magnetic field is the B1, and also here it is a B2. We consider like this, and so here this correspond to the omega 0, and the B1 correspond to the omega 1, and B2 correspond to the omega 2. So it is by the vector sum, and as a new magnetic field, general new magnetic field is the omega, let's consider omega nu. Here, because H0 is that this Hamiltonian, H0 Hamiltonian is that like this, and so the other one and H prime can be write down in a different manner, and so H prime is that the 1/2, and also omega 1 minus omega 1 and omega 2 and omega 2. It is different. It is different additional Hamiltonian. This additional Hamiltonian is very small comparing to the original Hamiltonian. So we can define that here it is a new Hamiltonian is that new Hamiltonian is that omega nu and Sn. Here Sn is a general spin, and the general spin can be considered can be regarded as the general rotational spin. So in this case, 1/2 h bar and omega nu, and also general rotating spin can be written in the matrix cosine theta minus cosine theta, sine theta, and sine theta. Here, here in this case, it is a theta. So tangent theta is that omega 0 plus omega 1 and omega 2. Yeah, so it is omega nu. The amplitude is that omega 0 plus omega 1 square plus omega 2 square. So in this case, this new energy is the plus minus 1/2 h bar omega nu. So it is the plus minus 1/2 h bar and square root omega 0 plus omega 1 square plus omega 2 square. Then here we assume that h prime is very small, so in the magnetic field also, and the B0 is much higher than the B1 or B2. In other words, in the omega 1 is very small comparing to omega 0, and also omega 2 is very small comparing to the omega 0 also. And so because energy is like this, and this new energy is the plus minus 1/2 h bar omega 0, then it is 1 plus omega 1 over omega 0 square plus omega 2 over omega 0 square. So when it can be rewritten like this, h bar omega 0 and square root here 1 plus 2 omega 1 over omega 0 plus omega 0 square and omega 1 square plus omega 2 square. And because this term is very small and it can be expanded as a Taylor series, so plus minus h bar omega 0 over 2, and here 1 plus, because it is this term and 1/2, and 1 plus and small value, and small value something like this, and also this 1 plus like this, plus blah blah blah. So by the Taylor series, so here the first term is that plus, and the second term is the 2 factorial 1/2 and minus 1/2 and something like square, plus 3 factorial 1/2 minus 1/2 and minus 3/2 and something like cube like this, and this Taylor series. So the first term is that omega 1 over omega 0 plus omega 1 square plus omega 2 square plus omega 2 square over 2 omega 0. Then second term, it is minus 1 over 8 2 omega 1 over omega 0 plus omega 1 square plus omega 2 square over omega 0 square to the second to the square plus like this. Then it is plus minus h bar omega 0 over half and 1 plus omega 1 over omega 0 plus omega 1 square plus omega 2 square over 2 omega 0 minus, and also 1/8, then omega 0 square 4 omega 1 square plus, and also 4 omega 1 square plus omega 2 square over omega 0 third. It is the product between this and this, and also this term, this square, is very small because it is very small, and also it terms also very small. Yeah, so we can ignore this term. So and the plus blah blah blah, and we can ignore in the higher term. So let's only consider for the square quadratic term. So it can be approximated by the plus minus h bar omega 0 over 2 and 1 plus omega 1 over omega 0 plus. By combining these two terms, then it is 2 omega 0 square and omega 2 square, because omega 1 square can be cancelled with each other, and also this one and this one, and it can be cancelled with each other. So here when you written like this, and here it is exactly solvable E0, it is zeroth order energy, and we call it is first order energy because it is order of 1, and it's second order. It is a second order of the energy. So basically, when you see this, then this energy eigenvalue, energy can be written like zeroth order to the first order to the second order, and we omitted the higher order term to the third order like this. So in this case, then we can see that the higher order energy is much smaller because basically omega 1 over omega 0 and omega 2 over omega 0 is very small. So higher order also should be decreased more and more significantly. So basically, when you see this, the Hamiltonian can be separated by the exactly solvable Hamiltonian and perturbed Hamiltonian, small perturbed Hamiltonian, and generally it can be calculated by the in general Hamiltonian. General Hamiltonian can be extended as a Taylor series. In that case, and the higher order term can be neglected, and so first order and second order can be considered. In this case, and we can apply to the perturbation theory. It is basically a time independent perturbation theory, and I will going on to the general formulation of the perturbation theory.